Now, in this part, I'd like to give you some examples of existing antenna arrays and get you a little bit through time of how those things were developed and how did we end up with considering that solution for 5G today. So first of all, as I mentioned, antenna arrays is a very old concept, and there are two main application areas that we use them today. One is defense, and the other one is satellite communications. So in this example, you can see a bunch of antenna arrays today utilized in defense systems. And it's actually interesting to see the size of those systems. So this antenna array here, it's basically a little hard to give you the scale of that, but a human being would likely be something like this. So those type of antenna arrays are outputting immense amount of power to basically detect threats from far away. And as you can imagine, this type of antenna array can actually scan with an amazingly small beam width. And we have learned in this class why this thing has to be large, right? So we have learned that the beam width will actually be proportional to the diameter of this thing, right? It's the same idea of creating an aperture, except now you can control the pixel of the aperture, all pixels of the apertures. Military aircraft have this type of antenna arrays to detect threats, and other aircraft. And even in radar systems, in civilian systems, we will actually use this type of antenna array sometimes. The same thing is true for satellite communications, and I would say the satellite communication people have done what we are trying to do now for 5G long time ago, and they've actually done it very well. So instead of sending basically one big beam to cover the entire United States, they actually sectorize the United States, and they give you multiple beams. And the reason that they have to focus the energy on each one of those cells is simply because they have to increase the gain to cover a few thousand kilometers that they have to cover. So the concept is identical to what we have been doing in satellite comm. The only difference is that now in 5G it becomes easier because the distances are far smaller. But of course, you're also outputting much less power to do the same thing. So the reason I'm saying that is because, again, we didn't suddenly wake up and said, hey, let's do antenna arrays. We already know they can work. So if you ask the question of why we didn't do it sooner, well, the reason that we didn't do it sooner was simply one, cost. The cost of the systems that you saw before is simply immense. We are talking about hundreds to thousands of dollars per element of the array. So only the defense people could afford it, and only satellite communications could basically afford it. So what suddenly happened, and we can basically bring the cost down, is really an interesting story. There are actually two things that happened over time, and we brought the cost down. The first was the immense advantages in the silicon and silicon germanium technology. Essentially, what people started doing is they started realizing that I can integrate everything I need in a single chip. So for example, this is an 8-channel transmit-receive silicon chip that now does a 2x2 dual polarization. You can actually see the system diagram here. And by the way, you can understand some of the system diagram here, but we will do more system analysis in the second part of this course. But the whole point is that now I can integrate everything into a single silicon chip, and that means I can produce it inexpensively and at a very high yield and massively. So you can imagine this as being the heart of the antenna array. But you don't just need the silicon chip to make this thing work. You need everything else around it. So what else do you need? You need to be able to produce PC boards where here, for example, antenna elements printed on a PC board. And you need to produce basically this type of antenna arrays on PC boards at a very high quality and a very low loss and very inexpensively. So the PCB technology simply has advanced dramatically over the last 2 to 3 decades. You have to be able to package those silicon chips in ways that essentially make them reliable. In fact, these antenna arrays today that you can use them in airplanes, they pretty much have the same lifespan as the plane itself. So you don't have to worry about changing it ever. I already talked about, in general, the silicon and CMOS advantages. Essentially, it allowed people to push their designs to the microwave and millimeter wave range. Just to give you an idea, 20 years ago, it would be very hard to find any CMOS process that will give you an FT of a transistor that would be in the order of a few tenths of gigahertz. Now you can actually exceed 100 gigahertz. And so that means that the silicon people came up with this amazing technology to allow you to design microwave systems at a very, very low cost process. And honestly, the other part is the analysis tools. The analysis tools we have today, and we have it, all of us, in our desks, essentially allow us to make the design very precise and practically guarantee a first pass success. 20 years ago, 30 years ago, we couldn't do that. Nowadays, you basically buy a good license of a software, and your design is successful the first minute. So when you combine all of this together and you put a massive industry behind it, you basically get what I'm talking about. So here's essentially a few examples of antenna arrays that exist right now using this idea. So when you just look at them, they will appear of something of this nature that you see here. Is basically a PC board with a massive number of elements, but the complexity of that PC board is amazing. And it's amazing both from a design perspective as well as from an implementation perspective. Here's another example of such an antenna array that has been produced today, both communication as well as satellite, and in the future, shortly, 5G. But what is also a little hard to see in those systems is that that system works uncalibrated. And that was actually a surprise for me as well when I started reading about this technology. Uncalibrated means I basically put it together, turn it on, and it works. In the old days, it used to be that once you make this antenna array, you had to spend a couple of months calibrating it, which would add immensely to the cost. Right now, it simply works. Now, does it mean there is no silicon to silicon variability when you go from one chip to the next? No, there is quite a bit. But it is sufficient to basically make a large antenna array work. And so that's really the main reason that people are using that. Now, it doesn't mean that all antenna arrays will be uncalibrated. There is actually people who are thinking about self-correcting factors and self-calibration techniques. But in general, the amazing success of first-pass design basically makes this cost bearable by everyone. Here's an example of a 60 gigahertz antenna array that was actually coming again from Professor Abay's group at UC San Diego. You asked me before about the size of these things. So here's basically how small an antenna array could be. Essentially, a lot of different people are producing those from industry today, and the performance will only improve over time. This is an interesting example of a demonstration that actually happened at UCSD. They basically took the antenna arrays that they're producing, and they basically made a simple link, 300 meters. Essentially, they tried to see how well the system works. This is the signal constellation that was measured. Again, go back at the beginning of this class, and you will see that we covered signal constellations and what those things mean. So you can see, for example, that at 0-degree scan here, we're achieving 400 megabps. Here we're achieving 1 gigabps, and so on and so forth. The interesting thing, however, there is that the link worked really well. And so despite the path loss of 111 dBs, they were able to essentially utilize two 4x8 antenna arrays in the transmit and receive side, and the system was an amazing success. So essentially, it shows that yes, very high data rates in the order of a gigabps can indeed be transmitted over a 300-meter link. This is an example that actually shows you a little bit of more detail of the antenna array at this system. So here's a picture of the antenna array that they utilized. And this guy here, this diagram here, shows you essentially the scanning angle of this antenna array. So as I mentioned before, plus or minus 50 degrees is pretty typical. And this, you can see here the main beam moving back and forth. Also notice a couple of other interesting things. First of all, notice the side lobe level. So side lobe essentially is the next lobe next to the main beam. So you can see, for example, here in this line, the side lobe level somewhere here is in the order of 15 dBs. Most of the side lobe levels here are between 15 to 20 dBs. Now, that is actually a direct result of having what I was mentioning before, this uncalibrated performance. The reason you have the side lobe levels and you can't bring them down to, let's say, negative 30 dB is because there is a little bit of a phase error when you add or subtract the paths, and that phase error cannot be corrected if you do the uncalibrated performance. But if you do the calibration, and in some applications you do need that, for example, in satellite comm, we often have to get a a side lobe down to the 30 dB level because we can't radiate somebody with too much power, then you actually do need a calibration and get this thing done. But in most applications, I would say the side lobe level in the order of 20 dB is more than acceptable. And that shows really the promise of having these things potentially work and calibrated.